Okay, in this video we're going to look at a very beautiful result from elementary number theory called quadratic reciprocity. Okay, so let's look at the statement. First, let's recall that these are Legendre symbols, so they answer a question: is P a quadratic residue mod Q, or is Q a quadratic residue modulo P? And I'll let you look on previous videos to look more about quadratic residues. So let's look at the theorem. So let's say P and Q are distinct odd primes. Then this P on Q times Q on P, where those are Legendre symbols, is -1 to this product P minus 1 over 2 times Q minus 1 over 2. And then that happens to be equal to 1 if P or Q is congruent to 1 mod 4. And it's -1 if P is congruent to Q is congruent to 3 mod 4. So what we'll end up proving is this first equality. That's the hard part. It's actually pretty easy to prove the second equality just by the form of these primes and the first equality. Okay, so what we'll need as a tool to prove this theorem is the following lemma. So if P is an odd prime and A is an odd number not divisible by P, then you set N equal to this technical sum. Notice it's the sum from J equals 1 to P minus 1 over 2 of the floor of J times A over P, and then you get this Legendre symbol of A by P is equal to -1 to this power n that is constructed via that sum. So before we look at the proof of the lemma, I want to look at a calculation example of the lemma. So let's say we have P equals 13 and A equals 9. So that definitely satisfies the lemma. So we have an odd prime, and then we have an odd number not divisible by the prime. So in this case, we have n equals the sum, j equals 1 to p minus 1 over 2. So that's going to be 13 minus 1 over 2, or in other words, 6. And then we have 9 times j over 13, and we take the floor of that, or the greatest integer function. Okay, good. So now notice that's equal to the floor of 9 over 13, plus the floor of 18 over 13, plus the floor of 27 over 13, plus 36 over 13, plus 45 over 13, plus 54 over 13. So notice we have the sum from j equals 1 to 6. But now notice, taking each of those floors, we get 0 plus, this one's 1, plus the next two are 2. Good, and then we have plus 3 plus 4, plus 3 plus 4. Okay, good. But now notice that adds up to 12. And so that also tells us the following, that the Legendre symbol 9 by 13 is equal to -1 to the 12. In other words, 9 is a quadratic residue mod 13, but that's sort of obvious because 9 is equal to 3 squared mod 13. Okay, good. So now I'll clean up this board and then we'll look at the proof of this technical lemma. Okay, so let's look at the proof of this lemma. So we're going to start off by being motivated a little bit by the proof of Gauss's lemma. I have a video of that if you want to check it out. So what we want to do is consider the least non-negative residues of these numbers A, 2A, 3A, all the way up to P minus 1 over 2 times A. So we've got P minus 1 over 2 non-negative residues, and now I want to split these into 2 sets. So I want to split these, one into the set where they are greater than P over 2, and I'm going to call those R1 up to Rn. And then I also want to split it into the set that's less than P over 2, and I'll call those S1 up to Sm. Okay, good. And now let's recall from Gauss's lemma, we know that a by p is -1 to the little n, and we'll actually use that in the very end. Okay, good. So now the next thing we want to do is notice the following. So now for j equals 1 to p minus 1 over 2, we can write the following. J times a equals p times the floor of ja over p plus some remainder. So here we just use the division algorithm with p and j times a. Okay, great. And now notice this remainder is going to depend on j. In other words, it's going to depend on this number that we're indexing through. Okay, great. And also notice that as j indexes from 1 to p minus 1, we are going to achieve the numbers r1 through rn and s1 through sm exactly one time in this list. So let's write that down. Each of r1 to rm and s1 to sm appears exactly once in this list. Okay, good. And so now notice that we can add all of these equations together using this fact to get the following. So that'll give us the sum j equals 1 to p minus 1 over 2 of j times a. And then it also give us on the right hand side the sum j equals 1 to p minus 1 over 2 of this p times the floor of ja over p. Great. And now we're going to add up all the remainders. But now notice each of these remainders appears exactly once. So that'll give us the sum of all of the r's and all of the s's. So that'll be plus the sum j equals 1 to n of these rj's plus the sum j equals 1 to m of all of these sj's. Okay, good. So now what I'll do is I'll bring this sum up to the top and then we'll continue on with the proof. Okay, so I've brought this sum up from the bottom, so let's just recall it's the sum from j equals 1 to p minus 1 over 2 of ja. And that's going to be the same thing as the sum from j equals 1 to p minus 2 of p times this floor of ja over p plus the remainders. And the remainders split into these two cases, so the rj's and the sj's. And let's recall that the rj's were all of the non-negative residues that were larger than p over 2, and the sj's were the ones that were smaller than p over 2. Okay, good. And I've labeled that equation number 1. Good. So now the next thing I want to notice is the following. So this comes from the proof of Gauss's lemma. So like in the proof of Gauss's lemma. So again, I'll let you guys look up that proof if you need to. I have a video of it. So we get the following. This set 1, 2, 3 up to p minus 1 over 2 is exactly equal to this set p minus r1, p minus r2, up to p minus rn, and then s1 to sm. So remember that s1 to sm are already smaller than p over 2, so they're smaller than or equal to p minus 1 over 2. And then if we subtract these rj's from p, they're also going to be smaller than or equal to p minus 1 over 2. And then it's kind of easy to check that none of the numbers of this type are equal, none of the numbers of this type are equal, and then none of the numbers of the opposite type are equal. Again, I'll let you look at the proof of Gauss's lemma in order to check that. Okay, great. So now let's notice what we can do with that. Now we can take the sum, j equals 1 to p minus 1 over 2, which is actually just the sum of everything in this set. So we're taking the sum of all of these j's. But notice that's exactly the same thing as the sum j equals 1 to n of p minus rj plus the sum j equals 1 to m of sj. Okay, cool. But now notice, this is easy to calculate because we have n p's. So this is p times n minus the sum j equals 1 to n of rj plus the sum j equals 1 to m of sj. Okay, and I'm going to number this as well. So I'll number this 2. And the next thing that we'll do is do equation 1 minus equation 2 and see what we get. So notice here we have the sum of j times a, and here we have the sum of j. So that means we can factor an a minus 1 out of that. In other words, factoring a j out of that, and we get the sum. So we get a minus 1 times the sum j equals 1 to p minus 1 over 2 of j. Good, that's what we get for the left-hand side. And now notice for the right-hand side, some stuff cancels. In fact, these sj's cancel, and we're left with the following. So we're left with plus the sum j equals 1 to p minus 1 over 2 of p times the floor of ja over 2. Sorry, over p. Good. And then next we're going to have minus p times n. Okay, good. And then plus 2 times the sum j equals 1 to n of rj, because we have this term and this term adding up, and then since we're subtracting, that turns into a plus, and we get 2 of them. Okay, good. So now I'm going to move this 1 minus 2 equation up to the top, and we're almost done with the proof of this lemma. Okay, so now we're almost done with the proof of this lemma. So let's recall that we subtracted 2 equations on the last board, and we got the following. A minus 1 times the sum from j equals 1 to p minus 1 over 2 of j was equal to this term. But now notice this technical sum involving the floor was exactly equal to this capital N that we defined in the statement of the lemma. So I've simplified this by writing this as p times n minus p times little n. And remember, little n were the number of non-negative residues that were larger than p over 2 of a certain list. And then plus 2 times the sum of all of these rj's. And so now we're going to reduce this whole equation modulo 2. And you might ask, well, why are we going to reduce modulo 2? And that's because we are putting it in the exponent of negative 1. And recall that exponents of negative 1 will obviously work modulo 2. If you have negative 1 to an even power, you get a positive 1. Negative 1 to an odd power will give you a negative 1. So now notice, since a is odd, a minus 1 is even, and so that makes this left-hand side equal to 0 mod 2. Good. And then also, over here we have p as an odd prime, so that means p is congruent to 1 mod 2, so we get n. And then here we have the same p, so that's minus little n, and now we have 2 times a number, so that is plus 0. So notice, in this case, we get our capital N equals the little n, which again, the little n is as described earlier in the proof. And so, by Gauss's lemma, we have this Legendre symbol a by p is equal to negative 1 to that little n, where again that little n is defined as it was earlier in the proof, which is equal to negative 1 to the capital N by this argument that we just made. And this finishes the proof of this technical lemma. Okay, so now I'm going to clean up the chalkboard, and then we're going to move on to the proof of the quadratic reciprocity theorem. Okay, now before we get started with the proof of quadratic reciprocity, I just want to point out what it says again, because I'm going to have to erase this board. Usually I like to leave this up, but I'm going to need the whole board for the proof of the quadratic reciprocity. So let's look what it says. If P and Q are distinct odd primes, then the Legendre symbol P by Q times Q by P is -1 to the P minus 1 over Q2 times Q minus 1 over 2, and that's equal to 1 if at least one of them is congruent to 1 mod 4, and it's -1 if they're both congruent to 3 mod 4. And along the way, we'll use this technical lemma that we just proved, where if you define this capital N as this sum of these floors, then A by P is equal to -1 to this capital N. Okay, good. So now I'm going to finally get the board all cleaned up and prepped for the proof of the quadratic reciprocity theorem. Okay, so now we're ready for the proof of the quadratic reciprocity. So I've prepped the board with this figure. And so let's see, we start off with outloss generality. We assume that P is bigger than Q. So notice they're both distinct odd primes, so one has to be larger, so we'll just assume that P is larger. And now the next thing is we consider this array. So notice this is a P by Q box, and in it we have all of these lattice points. In other words, those are places where each coordinate is an integer. So this would be like the coordinate 0, 0. This would be the coordinate 2, 1, and so on and so forth. Up here would be the coordinate PQ. Okay, good. So I've put all the lattice points with these dotted lines and these blue dots as where they intersect. And then the other thing that we want is we want this line segment from the origin to this point N up here, which is P times Q. Good. And then we also want a perpendicular line up from P minus 1 over 2 to intersect at this point M. Good. And then this perpendicular line out from Q minus 1 over 2 that's going to intersect here at P and here at B. Okay, good. And then our strategy will be to count the number of lattice points in this rectangle OABC 2 different ways. And we also don't want to count all of them. We want to count the ones that include all the points on the segment AB, so on AB and BC, but off OA and OC. Good. So in other words, we want to include the ones not on these coordinate axes, but yes on these kind of end sides here. Okay, good. So method number 1 for counting is just like straight up multiplication. So it's like sort of obvious that just by multiplication, we get the following. This is clearly P minus 1 over 2 times Q minus 1 over 2. Because here we have 1, 2, 3, up to P minus 1 over 2 lattice points on this segment, and then we have in total Q minus 1 over 2 segments. Okay, good. So method number 2 is obviously going to be a little bit more intricate, but we'll create an equation that will involve this first method and allow us to prove our result. Okay, so method number 2 notices these following facts. So the line segment ON from the origin to N has the following slope. So it has the slope Q over P. Good. And then since Q and P are both primes, there are no lattice points on this segment. So there are no lattice points on ON, which is nice because then we don't have to worry about counting them. So notice in my picture it looks like there's lattice points on ON, but that's just because of the visualization of the program. It's not because of there are actual lattice points on ON. Okay, good. And now let's just suppose that there were lattice points on ON. Then I think you could prove that Q and P were not relatively prime, which would obviously be a contradiction. The next thing that we're going to notice is that the y coordinate of M is the following. So how we're going to do that is notice that this is on a line with a slope of q over p, and its x-coordinate is p over 2. So that means its y-coordinate is q over p times p over 2. Sorry, p minus 1 over 2. Okay, great. But now notice we can simplify that as follows. That's the same thing as q over 2 minus 1/2 q over p. Q over p, good. So next, we're going to also notice the following. This y-coordinate is between the following 2 points. So it's between q minus 1 over 2 and q plus 1 over 2. Okay, and so how do we see that? Well, we can figure out an inequality. So we have q minus 1 over 2, so that's less than q over 2 minus half. Okay, good. But now that's less than q over 2 minus 1/2 q over p, because we know that q over p is less than 1 by this assumption. Okay, good. But now that's less than q over 2. Okay, great. But now that is less than q plus 1 over 2. And now notice what we wanted was this was between these two, and we've got it. Okay, good. So now I'm going to clean up the board, and then we're going to pick up at the next step of the proof of this theorem. Okay, so now we're ready to continue with the proof. So now notice everything that we've done so far implies the following. There are no lattice points on this triangle MPB. Good, except possibly on PB. Okay, so let's see why that's the case. So notice we just showed that there were no lattice points between here and here, because this point right here was between q minus 1 over 2 and q minus 1 plus 2. And so here we have a lattice, we have a potential lattice point right here, but nothing on this segment. And furthermore, there was nothing on this segment because it's on this diagonal. And so all that leaves is this segment for the possibility of there being a lattice point. Okay, good. So now thus, we have the following. So number of lattice points in the rectangle that we want, OA, B, C, on AB and BC, off OA and OC. So remember, that's our goal. So that equals, so the number of lattice points in triangle OPC, off OC, okay, good, plus the number of lattice points in triangle OAM, off OA. Okay. Good. So let's look at that. So notice the whole rectangle, good, from here to here, needs to be the same thing as this triangle plus this triangle. Now we just showed there was nothing up here in this triangle, so that means what's left over in this bit right here, which is not quite a triangle, is the same thing as what's left in this big triangle right here, this triangle OAM. Okay. Good. So that means we can start to count this. Sorry, this should be OAM. Okay, good. So now notice that this number is equal to the following. So this number is equal to the sum j equals 1 to q minus 1 over 2 jp over q, the floor of that. Okay, good. And then, so how do we get that? Well, that would be like the sum on, so let's see, we're looking at OPC. So that would be the sum on this first segment plus the sum on the second segment, all the way up to the sum on this top segment. And since we're starting at j equals 1, we do not include this line segment, which is the coordinate axis. Okay, good. And now let's call that thing N1. And now notice that this is equal to the sum j equals 1 to p minus 1 over 2 of jq over p, the floor of that. Okay, good. So what we're doing there is we're adding all of the lattice points on these segments going this way within this triangle. And again, it looks like we're overcounting because we hit this little bit up here, but we already argued there were no lattice points up there in that little triangle. Okay, good. And now we'll call this one N2. And so now notice, by counting these lattice points two different ways, we've achieved the following. N1 plus N2 equals P minus 1 over 2 times Q minus 1 over 2. Okay, good. And now, furthermore, we have the final blow, which is P by Q times Q by P. So that's going to be equal to -1 to the N1 times -1 to the N2. Okay, good. And that's by our technical lemma. Okay, good. But now that's also -1 to the N1 plus N2. But now we can replace this N1 plus N2 with this product. So we have -1 to the P minus 1 over 2 times Q minus 1 over 2. And that finishes the proof.